Welcome to this presentation on linear time invariant systems. My name is Kannan Moudgalya. The outline of this presentation is as follows. We will talk about the linearity of a function, then the linearity of a system that has two functions. We will discuss input output linearity. We will also discuss superposition principle. We will conclude this with time invariant systems. Recall the standard definition. A function f is said to be linear if f of alpha x1 plus beta x2 equals alpha of f of x1, the same alpha should come here and the same beta should come here. Alpha and beta are arbitrary scalars. Here is the example of a linear function. F of x is equal to 2x. This is non-linear sin x. What about this 2x plus 3? You can verify that it is not linear. You will have to try this out. Basically on the left hand side you will get only 3, whereas on the right hand side you will get 6. This will produce a 3, this will produce another 3. So you will have 6 on this side, whereas you will have only 3 on this side. That is why these two are not equal and hence this function is not linear. Now let us consider a system that has two functions which are future states and outputs. This system is indicated by this rectangular box. It has two inputs. One is the initial state as mentioned here. The other is the input which is applied from n equals n0 onwards, and we measure the state and the output y, and these are described as follows. So x is future state and y is future output, and x and y are defined by the standard equations. We derived them in the previous lectures. So we say that this system itself is defined by these two equations, namely state equation and the output equation. For a system like that, we will discuss linearity. We will use the standard definition that we had stated in the first slide. So here are two cases. We apply this input given in blue, you get this output given in blue. These are the future states and future outputs. Here is the same system, but it is at two different inputs, namely the initial state is different. Of course they are both at n0 and another sequence u2 of n for all future values of n are applied, and you get the values indicated by red. So you give this in blue, you get this output, you get this in red, and you get this output in blue. Now the question is, when I take a times this plus b times this, will I get a times this and b times this? If so, we call the system to be linear. Remember the same linear combination, if I use a times this, I should get a times this in the output. Okay. Similarly, if I use b times this here, then I should get b times this output over here. Then we say the system is linear. So the question is, this system x of n plus 1 equals a n x n plus b n u n, is it linear? This equation is in the standard format. Alright, what do? We have to consider one x1 of n0 and u1 of n for all n greater than n0. and using this we calculate x1 of n0 plus 1. Similarly, do the same thing for x2, x2 of n0, u2 of n, this n greater or equal to this n0, and these two give rise to x2 of n0 plus 1. In other words, for this first set I calculated the next state, for the second state I calculated the next state. I call these x1 and x2. Now, to show that it is linear, I will take a linear combination of this input u, I will take the same linear combination of the initial state x. So, what do we have to show? We have to show that x of n0 plus 1, that is, if I apply these two, I get the corresponding next state to be this. Will it be a linear combination of the same alpha is to be used here and same beta is to be used here. When I give this, I got x1 of n0 plus 1, which comes here. I am using alpha times that, so I should multiply this by alpha, and these two give rise to this as given by this equation. Beta of this should give rise to beta of this. If I get this, then it is linear. What I want you to do is, I want you to substitute these values and verify that this is indeed true. Similarly, you can show that the output equation also is linear, and you can show this for all n values in the future. So, we call the system a linear system. Next, we go on to the case where we would like to consider the effect of only input. Here I call it y sub u. Y sub u is the output that I get when the initial state is 0. So, what does it do? Because the system is linear, when the input is doubled, this is not x2, it is doubled, when u is multiplied by 2, this x and y double. So, we have taken a linear system and we have taken this particular case where we have taken the initial state to be 0. Similarly, we consider the same system, but now we take the input to be 0, but we consider a non-zero initial state, and we call the corresponding output to be y sub x. This x indicates this response is due only to non-zero initial state. Now, what do I do? Let me add these two. So, I have to add this. Okay, what linear combination? I am saying this plus this, alpha and beta are 1. So, I am using alpha and beta to be 1 here also. In other words, just add them. Okay. So, we say that output y is the sum of output due to input, which is this, and output due to initial state, it is this. Now, suppose I double only this, I double only the input, but not the initial state. For example, I hold this constant, I double this. I hold this constant, but I double this. Then what will happen is, this would have doubled, but this would not have doubled. So, the sum does not double. Okay. So, we have to keep that in mind. There are cases where we would want the entire thing to double. How do we handle this? So, this is what I call as how to achieve linearity from input alone. It is obvious, you have to make the initial state to be 0. For example, I take the initial state to be 0, I apply u1 of n, I get this. I apply another input. Remember, the initial state, however, is at n0. Initial instant is n0, we are starting the experiment at n0, but the state is 0 to start with at that instant. I give one input, I get this output, I give another input, another experiment on the same plant, I get another output, Now what will happen if I take a linear combination of these two? Will I get a linear combination of this and linear combination of this? The answer is yes, because the system is linear with respect to this is linear, this is linear. So it will use the same linear combination as this will use the same linear combination as this, okay. Remember that we are keeping this at 0. So it is linear from input output perspective. What does it mean? Let us go to the next slide, where I do not care about the initial state, I take the initial state equals 0. When I consider a linear combination of inputs, I get the same linear combination of outputs. So unless explicitly stated, we will assume 0 initial state. The word LTI or linear time invariant would imply that we have made this assumption. The moment we say LTI, we mean that the initial state is assumed to be 0. The next question is, what do we do if the initial state is not 0? It is very easy. Take the initial state to be 0 first. We have input output linearity as I explained earlier, and call the resulting output to be YU. So these are all linear. Then separately evaluate the output only to non-zero initial state, call it Yx. Now if you want to know the effect of these two together, then you add them, y equals y sub u plus y sub x. Remember, when you measure Yx, you have to keep the input to be 0, that is the meaning of y sub x. It is the output only due to the non-zero initial state. We will refer to this as the application of superposition principle. Next we will take up the concept of time invariant system. Consider the same state, it is initially at time instant n0, the state is x0. So what do we do? Now I take the same state x0, but at time instant n0 minus k0. In other words, suppose we do this experiment on Monday, and this is the experiment that is done on Tuesday, okay. But the starting state is the same, x0. On Monday 8 o'clock onwards, I start giving this input alpha, beta and so on. On Tuesday from 8 o'clock onwards, I start giving these values A1, A2 and so on. I get the corresponding outputs, I measure them, I call them with this, I color them with blue, here I color them with red. Given that this U2 is a shifted version of U1, it is a time shifted version of U1, shifted by the same amount here as here, then are the following satisfied? Is x2n, x1 of n minus k, and y2 of n equals y1 of n minus k. So that is the question, okay. So of course you have to be consistent. If you choose k0 here, you should keep k0 here. If so, the system is time invariant. It is illustrated graphically here. I do the experiment on Monday, I get this output. I do the same experiment on Tuesday. Remember, the starting value has to be the same. Then do I get the same shape? If so, the system is time invariant. I have some examples here. Y of n equals n into u of n is not time invariant. You can verify this, whereas our standard system is time invariant. You can verify this. With this, we have come to the end of this presentation. Thanks for joining.